All right, next we have the compiler SIG. Alex or Philip, and Alex was trying to present, but Philip, you want to do it?
All right, thanks. Yeah, so my name's Philip. I work at Grok as a compiler engineer, and I worked with Alex from IBM, who's also on the steering committee, to make this presentation, and we're both co-chairs of the ONNX compiler SIG. So this is our first time sharing ourselves with the community, so I'd like to just explain what our goals are first. So we want to make sure that the ONNX specification is both expressive and lean, making it tractable for hardware companies and compiler and runtime developers to implement this specification for a variety of hardware platforms. And so what that means to us is we want to make sure that the ONNX specification is unambiguous, it's lean, so that there's a refined set of ops, and also that it's well documented. And with some of the stuff I've seen earlier in some of these SIGs, I'm getting more confident that we're moving in the right direction. And what we also want to do is we want to build a shared compiler infrastructure. So we've been mainly focused on ONNX MLIR, but we also do things in terms of shape inference. So just a little bit of history. We started, a bunch of us worked together on ONNX MLIR, and we use that to brainstorm and come together. And this kind of spun out of the work we started there, but we wanted to expand to more than just ONNX MLIR. So the compiler SIG is an active community. We have many companies involved, including ByteDance, AMD, ARM, Grok, IBM, Microsoft, and NVIDIA. We have monthly compiler SIG meetings, the first Tuesday of every month at 8 p.m. Eastern time. And we also have weekly ONNX MLIR meetings on Tuesdays, and some of those times are Asian-friendly, and some of those times are European-friendly. And yeah, so in ONNX MLIR, we had 621 PRs over the last year. So I know we had one presentation so far about ONNX MLIR and specifically shape inference, but I'll give a really quick overview. So basically MLIR, which stands for the multi-level intermediate representation, is a set of extensible data structures and libraries used for building compilers. They've become pretty industry standard with many different companies using these libraries to build their compilers. So what ONNX MLIR does, and the biggest part of the shared infrastructure, is that it takes an ONNX file and it translates it into an MLIR dialect. And this is a part, and so that MLIR dialect is basically, it's basically an intermediate representation. Basically, if this wasn't part of a shared infrastructure, every MLIR compiler would need to do this part themselves. We also do a little bit more, which is we add shape inference, constant propagation, some canonicalization, as well as a variety of transformations and optimizations, often in the form of decompositions. We also have some lowerings to different dialects. So ByteDance contributed to an MHLow backend. AMD and ARM contributed a TOSA backend. And there's a draft for a Linalg dialect, and Microsoft has some interest in that and is also working with us on that. Then we also have some lowerings to CPU IRs, which IBM uses. And then we also have some people who use us, like Grok. We use it outside of the main repository, and so we have a lowering in our own code base. So I just want to give a quick case study on Grok. So we think of ourselves as basically a 320 SIMD engine, and we have multiple functional units and data streams across our chip, both left and right. So it's quite a different architecture than normal things. We also deterministic, so invocations take the exact same number of cycles every invocation of the program. One of the things about our architecture is that the hardware is relatively simple, but we give a lot of a lot of that information to software, which makes the compiler relatively complex. So our normal workflow is that we'll have a PyTorch model, and then we'll translate that to ONNX, and then we will use ONNXMLIR as the top part of our compiler stack, and then translate that to our high-level dialect G10. And then from there, we lower to our mid-level and low-level IRs before finally outputting an IOP that we can run on the Grok chip. And so the thing that made ONNX so appealing to us is it becomes pretty intractable as a chip startup to implement all of these torch ops. So having ONNX have a refined opset where, having a refined opset and also being stable was really appealing to us. What we want is our compiler engineers to be focused on these two parts of the stack, mainly these hairy low-level optimizations. And we are really happy that the open source ecosystem, mainly the ONNX ecosystem, takes care of the top part of the stack. And now I'll give the IBM case study.
Can you hear me?
Oh, perfect.
Excellent, just on time. Yeah, so IBM, basically, we use ONNXMLIR for two different purposes. One is to offer IBM servers like the top performance. And so here, we really want to get a single binary with CPU and accelerator code with no external dependencies. In some ways, our server like Edge servers, we want really a very tight and no dependencies on other things that may have a risk or security issues. So we wanted full control over the entire stack. And so ONNXMLIR is perfect for that. We optimize usage of the AI accelerator whenever we can because it's much faster. And also we do all the traditional things that you do with accelerators. We want to minimize data movements, data reorganization between CPU and AI accelerator. And for this purpose, the ONNXMLIR is a perfect, and MLIR in general is a perfect medium for that. And then we also try to offer things to the community. And so basically, the CPU code can run on any LLVM supported platform, Mac, Windows, Linux, those are the operating systems, but basically a lot of different machines. So it can be used to run CPU code because the accelerator doesn't run everything. And we wanted anyway compiled version of all the code as a reference. And finally, for accelerator, so we structured it as a template so that if other companies are interested in getting something similar to what we have, they can potentially reuse and isolate their case within the ONNXMLIR code base, but as a separate accelerator. Thank you.
Thanks, Alex. So far over the last year, we've done a lot in ONNXMLIR specifically. We've upgraded it from OPSET 13 all the way to supporting the ingestion of OPSET 18. We've also we've made the compiler dramatically faster. And there's many more things that we're working on. And in the coming weeks, we expect to have support for function decomposition and function inlining. And so the aspirations for the compiler SIG is that we want to be more proactive in the different SIGs, making sure that a compiler implementer voice is in there. And so we want to make sure that the new operators are consistent and unambiguous. We also want to make the current ONNX compiler infrastructure more attractive. And then finally, we want to reach out to other deep learning compiler platforms. I know this was heavily focused on ONNXMLIR, but we are aware there are many other compilers out there, including people working on Apache, TVM, and people on TensorRT. So we'd really love for them to join us in our meetings and that we can work together to make sure that ONNX works well for compiler implementers. Thanks.
Any questions for them? All right, thank you, Philip, and thank you, Alex, for representing the compiler SIG. So next we have the operator SIG, and there's a video. Let me put that up.
Hello, welcome. This is Rama from Microsoft. I will be giving this update on behalf of the ONNX operator SIG. Let me start with a summary of key changes over the last year since the last meetup. IR version 9 introduces 8-bit float types. There are 4 variants falling into 2 families, each planned to be supported by various hardware backends. The 2 formats are mostly similar, each supporting 2 variants with either 4 or 5 exponent bits. They all have 1 sign bit, with the remaining 3 or 2 bits respectively used as the mantissa bits. The differences relate to special values. In particular, 3 of these formats do not support infinity values, but they all support the NaN value. Further, 2 of these formats do not support a -0 and instead use that bit pattern to represent the NaN value. You can find more information about these formats in the links shown in the PowerPoint. As of now, no computation ops support the 8-bit float types. Instead, the plan is to rely on the QDQ representation that has been used for quantization so far. So the plan is to encode the computation by dequantizing the value before any computational op. The other extension in IR version 9 is support for representing default values of attributes in model local functions. Since the last meetup, there have been 2 new offsets, offset 18 and offset 19. These offsets introduce a small number of new ops as shown here. These include the element-wise bit manipulation ops, the MISH activation function, center crop pad, group normalization, call to M, and deformable convolution. Apart from the new ops, there have been some updates to existing ops. The pooling ops have been made uniform by adding some attributes to specific pooling ops that didn't support them. Similarly, reduction ops have been made uniform by making access as an input to all of these ops. The equal operator has been extended to support string equality. Pad and resize ops have been extended to support some new attributes, particularly motivated by pre-processing for images. The split op supports an uneven split, and generic ops like reshape have been extended to support the new float 8 types. One of the balancing trade-offs we run into ONNX is preventing an explosion in the number of ops that must be supported by various backends. One way we do this is by defining ops in the ONNX standard as functions or composite ops whenever possible. These are ops whose semantics can be expressed in terms of other, more primitive ops. This helps us keep the number of primitive ops that must be implemented by a backend small. Over the last year, a number of existing ops have been promoted into function ops. As of now, around 37 of existing ops are defined as functions. So what next? A couple of months back, we had a set of presentations by community members with their ideas to improve ONNX. You can find these presentations at the URL shown here. As a quick summary, there's a lot of interest in quantization. There's also interest in tokenization ops, attention ops, datetime parsing, and beam search. Let me take this opportunity to remind you that your contributions to ONNX are most welcome and appreciated. That brings me to the end of the presentation. Thanks for coming. Please get involved with the community. There are several ways to do this. Please contact us in the Slack channel if you have questions or comments. Feel free to create issues or PRs in the GitHub repo as well. We have monthly SIG meetings and everyone is invited to join these meetings. Thank you.
All right. Rama's on the call, so any questions for him and the operator SIG? No? All right.